This is the third lecture on advanced quantum mechanics. In the earlier class, we were discussing Dirac theory of relativistic quantum mechanics, and the last lecture was terminated abruptly due to some technical issues. Now we come to the we just start this class as a continuation of the previous class. So we conclude that alpha and beta could not be 2 by 2 matrices, so they are 4 by 4 matrices. So the option is they are 4 cross 4 matrices. Dirac quite arbitrarily assumed beta matrix to be a diagonal matrix. This is an identity matrix of order 2, and O2 is a null matrix of order 2. Here we have written the matrix in the matrix partition form, writing explicitly this is the form of beta matrix. And for alpha I matrix, alpha I means alpha I is equal to x. This is sigma I 0 sorry. This was the alpha matrices. For x I is equal to 1 stands for x, 2 is equal to y, and so on and so forth. These were the matrices. So we conclude that this is the linearized Hamiltonian as per Dirac, where this involves 4 operators alpha x, alpha y, alpha z, and beta. They are square matrices of order 4. They are square matrices of order 4 such that the squares of the matrix is unity, and they anticommute in pair, so that they are anticommute in pair. Their eigenvalues are plus minus 1 and the trace is 0. And the matrix is a 4 cross 4 matrix. This is assumed to be a theory which is valid for spin half particles, valid for spin half particles. And if we want to write this wave function in this equation, wave function, this is a matrix. This H is has 4 component matrices, so the wave function is a column matrix of order 4. They are called Dirac spinors. That is to say, psi is a square matrix, column matrix of which has 4 components, and this is known as Dirac spinors. If we were, just for information, if we have a particle of spin 1, then they are represented by a 10 cross 10 matrix. Now we do not move any further with the details of Dirac theory, but we come to the situation which is of our interest, that is, what is the implication of Dirac theory when it is applied to particle moving in central force field. To be specific, what would be the fate of a hydrogenic electron in Dirac theory? So first thing is, what would be the Dirac Hamiltonian in central force field? For free particle Dirac Hamiltonian is H is equal to mc square beta plus c alpha dot p. In central force field, represented by the potential V of R The Dirac Hamiltonian is V of R. We know from our study of classical mechanics that when a particle moves in a central force field, angular momentum is a constant of motion. So in classical mechanics, angular momentum L is R cross P is a constant of motion. In central field. What will be its implication in quantum mechanics? We found that in Schrödinger picture, theory, before going to that, the equation of motion in quantum mechanics is if the operator under consideration do not have any explicit time dependence, then this part goes, and we are left with the part that dA dt is related to the commutator bracket. For A to be a constant of motion, for A to be a constant of motion, one should have H, the commutator of the Hamiltonian with the operator itself, has to be 0. In Schrödinger picture treatment, that is in non-relativistic quantum mechanics, we found that H commutes with L square. H commutes with each of the Cartesian components of L, and that is the concept was retained that L is a constant of motion. We looked for simultaneous eigenvalues of H and we know that the hydrogenic wave function psi n L m is the simultaneous wave function of the operator H, L square and Lz. What is the situation in Dirac theory? So we are looking for the commutator of H with L, where H is this matrix. So in Dirac theory, our aim is to see what is the value of H, L, Lx in Dirac theory. This is our aim. So we start evaluating the matrix element. We consider the commutator of H with one of the component of L, say for example Lx. So we consider H, Lx. We are not writing the hats over the operator. So this is mc square beta tan commutator Lx, then this part c times alpha x px Lx commutator alpha y py Lx commutator plus alpha z pz Lx commutator plus v of r Lx commutator. These are the terms in both. You see that beta commutes with all the dynamical variables, so this is 0. Lx, if we represent it in spherical polar coordinate, the angular momentum components have only theta phi dependence, where for central force field potential has only r dependence, so this is 0. So we are left with this term. If we rewrite this term as c taken common, and you see that this one, if we take alpha x px Lx, this commutator can be written as alpha x px Lx plus alpha x Lx px. Here we have written this problem. ABC commutator is ABC commutator plus AC commutator B. This part. Since alpha and beta are constant operators, this part is 0, this part is 0, so we are left with alpha x px Lx commutator. This is applicable for all the three terms, so we write first one is alpha x px Lx, the second term alpha y Ly Lx, and third term alpha z pz Lz. Now we recall the commutator algebra that we have learnt in earlier classes, that is P alpha L beta is equal to sum over gamma RH cross epsilon alpha beta gamma P gamma. So in this sense, this is 1 1, which is 0, because the Lebesgue beta tensor with repeated index gives us 0 value. So Lebesgue beta tensor with repeated index gives us 0 value, so this is 0. For this it is 2 1, obviously 3, and you recall that epsilon 1 2 3 is equal to epsilon 3 1 2 is equal to epsilon 2 3 1 is equal to plus 1, and epsilon 1 3 2 is equal to epsilon 2 1 3 is equal to epsilon 3 2 1 is equal to minus 1. So this 2 1 3 it is minus. So this part is minus RH cross PZ, and coming to this part it is plus RH cross, because it is 3, sorry, this is X, 3 1, so this should be epsilon 3 1 2, epsilon 3 1 2 is plus 1, so RH cross it is py. So the quantity that we get is, we take minus IH cross common, minus IH cross C common, then we have alpha y pz minus alpha z py. This is minus IH cross C alpha cross p x component. That is, if we write a commutator of Hamiltonian with the vector L operator, this would be minus IH cross alpha cross p. This is one important relation. That is, we see that L, orbital angular momentum, is not a constant of motion and it is not equal to 0. So conclusion is orbital angular momentum is not a constant of motion in Dirac theory. So in classical mechanics, orbital angular momentum was the constant of motion. That concept was retained in Schrödinger picture, non-relativistic theory. But coming to Dirac's relativistic quantum mechanics, we see that the angular momentum, orbital angular momentum, is not a constant of motion. If we define a quantity, S operator is as h cross by 2 that is Sx that is Sx operator is defined as h by 2 where sigma x are Pauli spin matrices. With going through a bit of algebra, we can show that H S vector operator is plus IH cross C alpha cross P. Recall that alpha is related, this alpha is alpha x is related by these were the definition of alpha x. So if we consider these two equations, we see that H, you define a combined vector L plus S is 0, and we define this that H J vector operator is 0, where J, the vector quantity J, is called as L plus S and is called the total angular momentum or total angular momentum. So our conclusion is that we see that the orbital angular momentum is not a constant of motion in Dirac theory, and we have to add some quantity with the orbital angular momentum so that the resultant quantity becomes a constant of motion. And the quantity that has to be added is known as the spin operator already introduced. So we define total angular momentum J as the sum of the orbital angular momentum and the spin angular momentum. from this treatment we see that spin is a concept that comes from relativistic theory of electron. You do not have to add spin in an ad hoc manner in the theory to match the theoretical prediction with the experiment, but the existence of spin comes from the Dirac's theory as an automatic choice. We say that spin angular momentum is a quantity which do not have any classical analog. It is found that experimentally that for electrons spin has two projection values, one is plus half, another one is minus half, that is h cross by 2, plus minus h cross by 2. And the spin, so the quantum number associated with the s operator is s into s plus 1 square root of h cross, and the value of spin is half. If we want to match it with the spinning concept of Earth about its orbit, then we assume the electron to be an electron cloud, and from experimental data we estimate its approximate diameter. Then using that approximate value of the diameter, it is found that to have the spin value s is equal to half, the equatorial velocity, linear velocity of the electron charge cloud should be much greater than c, which is not physical. So we conclude once again that spin is a quantity which has its existence in relativistic quantum mechanics and has no classical analog. Now we come to the fact that what the Dirac theory gives us when we apply it to hydrogen atom problem. We have already said that this is the Hamiltonian for Dirac spin half particles when subjected to a central potential. For hydrogen atom problem, this central potential is Z e square by 4a epsilon 0 r. We are not going to the theory, just we shall state the result. It is found that the Hamiltonian or in central for hydrogen atom, Dirac's theory gives the Hamiltonian H is equal to minus H line square by 2 m As for Dirac's theory, the Hamiltonian can be written as this. This is up to v by c square order. It contains plus terms of higher order than v by c to the power cube, and higher order terms are included. We are not considering this. This is the non-relativistic Hamiltonian. This is the kinetic energy correction term. We know that the energy of a particle is m square c to the power 4 plus c square p square to the power half as per relativity. We write it as, taking mc square common, it is p square by m square c square to the power half. We expand this. If we this part this part is much smaller than 1, so we expand it binomially and retain only first 3 terms. So first term is 1, second term is p square by 2 m square c square, fourth term is half into 1 minus half by factorial 2, so this is minus 1 upon 8, p to the power 4, m4 c4 plus higher order terms. The first term is mc square, the rest mass energy. Note that we are writing m instead of m0. The second term is p square by twice m, the non-relativistic kinetic energy, and second term is p to the third term is p to the power 4, 8 m square. This should be 4, sorry, this is c cube, which is this term. So this is the first order correction over the non-relativistic kinetic energy term. This is known as the energy due to LS coupling term, LS coupling term energy. The angular momentum and spin, they interact with each other and giving rise to an interaction term. Note that J operator is defined as L operator plus S operator. So we define in terms of energy eigenvalues. This in vector notation we can write J dot J is equal to L dot L plus S dot S plus twice L dot S. So L dot S is equal to half J dot J minus L dot L minus S dot S. In terms of eigenvalues, L dot S term is half, this is H cross by 2 J into J plus 1 minus L into L plus 1, sorry, the eigenvalues J into J plus 1, these are eigenvalues, L into L plus 1 minus S into S plus 1. This is the LS coupling term, and this is, I will show you that this is not 0, and they gives rise to contribution in spin term. This term is known as Darwin term. This was originally a non-Hermitian term. Non-Hermitian term, then we generally make it Hermitian, and finally this is the form. We could find out the energy values by using perturbation technique. One way of getting the result is perturbation theory. If we consider this part of the Hamiltonian to be exactly solvable, then this part gives you the energy as we obtained in Bohr's theory or in Schrödinger picture. This much of the Hamiltonian gives you, this is known as Hamiltonian H0 minus H line square by 2m V of r. This is exactly solvable, and we know that H0 psi NLM is equal to E, it is the Bohr's theory. The energy depends only on the N, and this is NLM, where this is the Bohr energy or Schrödinger energy is given by minus RCH Rydberg constant times N square. This is a known part, and this part we can consider as a correction over the exactly solvable part, and this part is treated by perturbation theory. So we write, and it will be found that this part gives a energy contribution, which is the correction term E. This is due to the Dirac theory, and it is dependent on Nj, and explicit calculation shows that this is the energy contribution. This is, and if we add this with this, we get the energy of an electron as per Dirac's theory, which is correct up to order v square by c square. There are still other contributions which depends on v by c cube or still higher order terms. You see that the corresponding correction term as per Klein-Gordon equation, as we have mentioned. Here in Klein-Gordon theory, there were no spin, so it was J was replaced by L, and we write it as B Z alpha upon N square N upon L plus half minus 3 by 4. This was the correction over the Schrödinger energy or Bohr's energy as per Dirac theory and as per Klein-Gordon theory. We see that for a given value of n, L were the possible values of L were 0, 1 right up to n minus 1. So this energy was degenerate. Bohr's energy levels were degenerate with respect to L and M, but the L degeneracy, even for central potential, even for Coulomb potential, is resolved in Klein-Gordon theory and also in Dirac theory. As for a given value of n, J can have values half 3 by 2 and right up to n minus half. And these energy values, the degeneracy with respect to L is lifted in Dirac theory. But if we have, say, L is equal to 0, then as per Dirac's theory, J could have a value half only. And if we have L is equal to 1, then J, the possible value of J is half and 3 by 2. As for Dirac's theory, these two state for the same n, that is, if we call 2s half and 2p half, these two states will have the same energy as per Dirac's theory. So we are at a position to draw a conclusion on relativistic quantum mechanics. We started our discussion by saying that Schrödinger theory is not relativistically correct, so we introduced Klein-Gordon theory. But the Klein-Gordon theory, which is now believed to be applicable for spin zero particles, does not preserve the concept born interpretation for the wave function, as the probability density of Klein-Gordon theory is not essentially non-negative. It may be negative as well. So then Dirac came into the field and he linearized the Hamiltonian, and he wrote the Hamiltonian for free particles in this form, where beta and alpha are operators, constant operators. They are Hermitian operators, and they have the even ranks, and they anti-commute in pair and have their squares are unity. And we identified or construct the matrices, 4x4 matrices to represent electron, and these matrices, these 4 matrices can be constructed out of the known Pauli's matrices. Then we come to the Dirac Hamiltonian in the central force field, and we found that angular momentum is not a constant of motion, and we have to add something to the orbital angular momentum so that the resultant quantity is still a constant of motion, and that is the total angular momentum J is defined as L plus S, where S is the spin angular momentum that were introduced earlier. Now for hydrogen atom, the Hamiltonian of the Dirac Hamiltonian correct up to V by C square term is this. This is the non-relativistic Hamiltonian. This is the correction to kinetic energy. This is LS coupling term. This is Darwin term. Now this part, we solved this part in Schrödinger picture having this result, and this part could be treated via perturbation theory, and we get the, as per Dirac theory, the correction over the Schrödinger energy is given by this, where the L degeneracy is removed back, so the energy levels depends on N and J. But one problem, two states 2s half and 2p half will have the same value as per Dirac theory. The energy expression there could also be obtained without going to perturbation theory, and if we expand the complicated energy expression, which is correct up to second order in V by C, then we again get this energy expression. This is the all about relativistic quantum mechanics. In the next class we shall discuss generalized angular momentum.